Hi everyone, Neersha here, and welcome to a presentation on RoBERTa. We are called Group 11, and today we're going to dive deep into the advancements and optimizations that RoBERTa has brought to the BERT model. Before proceeding with RoBERTa, let's get a quick background on BERT itself. BERT stands for Bidirectional Encoder Representations from Transformers, and it is a model that revolutionized natural language processing because it is a model that can understand context from both directions. It is pre-trained on large datasets using two primary training objectives, NSP or next sentence prediction, and MLM or mass language modeling, both of which are shown um, in this diagram here. BERT uses transformers, particularly attention mechanisms, to capture the relationship between words in a sentence. And depending on whether it is BERT base and BERT large, it could have any number of these encoded layers. These encoded layers, the working inside of it is shown in this diagram here, wherein first we have three value, query, and key matrices that are created that undergo computations within themselves to finally give us an output of the encoded layer, of the attention layer in the encoder layer. So this model marked a significant improvement over traditional NLP models and set the stage for further advancements like RoBERTa. In BERT, we use the Adam optimizer, which has a peak with a peak learning rate of 10 raised to minus 4 and linear decay, and we train it for a maximum sequence length of 512 tokens with a minimax size of 256. And after every layer, there is a dropout of 0.1 and the GLU activation function. Okay, so now we can come to how exactly RoBERTa has made its improvements over BERT. RoBERTa stands for a robustly optimized BERT pre-training approach, and this name gives us the idea that they were trying to improve BERT through improving or changing its training process. So the modifications that they propose to make in the training are that we will train the model longer, we will take bigger batches and over more data. We'll remove the next sentence prediction objective entirely, even though the BERT paper has said that this is important, and we'll change the masking pattern from a static one to a dynamic one that we apply to the training data. Along with this, they also modified the hyperparameters that BERT was using. They changed the Adam epsilon term or the peak learning rate, and all of these factors were tuned separately for each setting, and they found that this was improving the stability of the model, whereas some hyperparameters were simply kept the same as BERT. So over the next few slides, my teammates will go over how exactly these modifications were made in the training and what was the impact. Thank you.
So now I'm going to discuss about the diverse and extensive datasets used in training the RoBERTa model. Language models like RoBERTa are data hungry, and their effectiveness not only depend on the methodology but also on the quality and quantity of data they are trained on. So we have used basically 5 kinds of dataset that amounts to 160 GB of text. So the first one is book corpus, which is a collection of over 11,000 freely available books. It covers a diverse range of narrative styles and topic, which provides linguistic structure to our language model. Second one is English Wikipedia. The content in the Wikipedia is present very well structured and in detail, so it provides us formal and structured way to our language model. The third one is Common Crawl Corpus, which collects millions of news from real world and which are the time sensitive information. The fourth one is Open Web Text, is a recreation of web text dataset used to train OpenAI's GPT model. It is a high quality web pages. It provides broad spectrum of language, of style and context. The fifth one is stories, in which the collection of stories is done through various websites that comprises fictional as well as narrative text. It provides complex sentence structures, narrative flow, and nuanced languages. So these combinations of large and diverse datasets enable RoBERTa to outperform on existing models and benchmarks like Glue, Squad, and Race. So next comes the input formats. So the first RoBERTa is takes input in the form of sequence or pair of sequence. So we have compared a few other input formats. The first one is segment pair, in which a segment, which is a collection of multiple sentences, come together with another segment and whose length must not be exceeding 512 tokens. And we retain the NSP loss in this case. The second one is sentence pair. So we take a pair of sentences whose length shouldn't exceed 512 token, but in this case the length is significantly shorter than 512, so we increase the batch size so that the total number of tokens remains similar to segment pair. In this case also we retain the NSP loss. Next one comes full sentences. Each input is packed with full sentences. The total length is at most 512 sentences. In this case, input may cross document boundaries. So the input may come from one or several documents. The last one is doc sentences. The inputs are similar to full sentences here, except the fact that they cannot cross document boundaries. So all the input will be coming from one single document itself. In both the cases, in full sentence and doc sentences, we remove the NSP loss.
So during pre-training, BERT uses two objectives. The first is the mass language model MLM, and the second is next sentence prediction NSP. So basically, MLM teaches BERT to understand relationships between words, while NSP teaches BERT to understand the long-term dependencies across sentences. So in the BERT model, the MLM model, what it does was that it takes 15% of the tokens, and out of those, 80% were replaced with mask. The remaining 10% were left unchanged, and the rest 10% were replaced randomly with some other vocabulary tokens. For the NSP, we had two sentences A and B, which and the input uh, was whether the B sentence followed the sentence A. So the BERT model outputted either true pair or false pair, depending on whether B was actually the sentence following A or not. So for the mass language model uh, objective, in the BERT model, it used static masking. Basically, in static masking, before training, we masked the sentences. To get better results in BERT, we duplicated the sentences 10 times over the 40 epochs of training. And in the RoBERTa model, the suggested change was to use dynamic masking instead of static masking, in which the sentences were masked on the go, like as during training process, when we saw a sentence, we used masking at that time in RoBERTa model. So basically, what that helped was that if the same sentence appeared twice in the training phase, in BERT, what it was that we had the same masking pattern because the sentence was already masked before training. But in RoBERTa model, since we are doing masking on the go, so the same sentence, if it appears twice, we have two different masking patterns. So that helped the result, the RoBERTa model train on less duplicated data during training, giving it an opportunity to work with more various data and masking patterns. For the next sentence prediction, NSP objective, two sentences A and B were given. While there was a 50% chance that B was the actual sentence following A, which was labeled as is next, there was a 50% chance that B was some random sentence chosen from the corpus. It was labeled as not next. So for our sentences, we had basically three special tokens. The CLS token was used to represent the start of the sentence. The SEP token was used to represent the separation between the sentences. It was also used to represent the end of the sentence. Although in some cases a special token EOS was used to represent the end of the sentence. The BERT paper, what it claimed was that removing NSP hurts performance with significant performance degradation. However, the RoBERTa paper contradicted this statement and suggested that removing NSP does not lead to significant performance issues, while in some cases it even led to a betterment of the downstream task. As discussed before, we had compared the 4 different input comparisons. So basically the doc sentences performed the best. However, the doc sentences, since we were padding at the end of every document, so it took a lot of time. While for full sentences, the performance gap between full sentence and doc sentence was not pretty large, and full sentences were comparatively faster since we were not limiting to the end of the document. Hence, in our model, RoBERTa used full sentences.
Next, we'll look on the effects of training the model with larger batch sizes. So basically, training the model with bigger batch sizes, as in the previous researches, has also shown that it leads to better training speed and also the end task performance. And the same research was applied on BERT, and for BERT also, it was shown that training the model with larger batches was found helpful. The technique of gradient accumulation was used so that the computational cost doesn't exceed or increase much for while using the larger batch sizes. Actually, the technique of gradient accumulation ensures that the computational cost actually remains as it is and doesn't increase beyond a certain limit. And one more a benefit of using large batches was like you can distribute your training over various multiple machines, which can make your training speed faster and also which will make your training more scalable over the various machines. So this is a table which shows that varying the batch size and also the steps and its effects on the model. You can see as we are increasing the batch sizes from 256 to 2000 and further to 8000, we are getting a better result. Actually, the optimum result are achieved when the batch size is 2000 and the step size is 125K. Perplexity, as you can see, for 2000 is the lowest, which is actually preferable, and we thus conclude that larger batch size is good for our model. Next, we'll look at the text encoding techniques which are used for RoBERTa. Uh, the basic technique which are used for both BERT and RoBERTa is byte pair encoding. We'll first briefly look at what byte pair encoding is. Byte pair encoding is basically encoding between character level and word level representations. The vocabulary size of byte pair encoding can vary from 10K to 100K. It depends on how we are training our model. But one important thing to note that most of the vocabulary size comes from Unicode characters so which make, especially when we are training our model over a large data set. And now looking at how the byte pair encodings differ for BERT and RoBERTa is that BERT implementation using character level BPE, which is vocabulary size of 30,000, and for that you need to pre-process the input with some heuristic tokenization rules. But whereas for RoBERTa we use something called as byte pair encoding, which basically here the smallest unit of tokenization is not the character but byte itself. Byte Taking byte as the smallest unit of tokenization helps is because anything or any text in particular in any language can be represented in form of bytes, is ultimately represented in form of bytes. Using bytes does increase our vocabulary size to 50K, which increases the model sizes and obviously the parameters of the model. But also while comparing the performance of two, the byte level approach results in a slight decrement in the performance, but this decrement can be overlooked because of the fact that the byte level encoding is actually more universal, and it is easier for a model like RoBERTa to process any of the language which needs to be processed further.
Now, I'll be discussing the evaluation of RoBERTa across three significant NLP benchmarks, which are glue, squad, and erase. Let's explore the tasks involved in each benchmark, how RoBERTa performed, and what the results mean in the context of language understanding. Firstly, the glue benchmark. The glue benchmark, that is short for General Language Understanding Evaluation, is a collection of 9 diverse tasks designed to evaluate various aspects of natural language understanding. It is a comprehensive benchmark that assesses models on key NLP capabilities such as sentence classification, textual inference, and sentence similarity. Some notable tasks include MNLI, which is multi-genre natural language inference. Here, the model determines whether the premise entails, contradicts, or is neutral towards a given hypothesis. Another task is QQP, that is Cora question pairs. It determines if two questions are semantically equivalent. Another task is COLA, that is Corpus of Linguistic Acceptability, a task for judging whether a given sentence is grammatically acceptable in English. For evaluating models on glue, two fine-tuning settings were considered for RoBERTa. Single task fine-tuning, that is development stage. In this setting, RoBERTa is fine-tuned separately for each individual glue task using only the training data for that task. The second setting was ensemble-based evaluation. In this setting, RoBERTa is evaluated on the glue test set and compared with other approaches via the glue leaderboard. Many leaderboard submissions rely on multitask fine-tuning, but RoBERTa's submission is focused solely on single-task fine-tuning. Next, we have the SQUAD benchmark, which is short for Stanford Question Answering Dataset, which evaluates a model's reasoning comprehension abilities. In this task, the model is presented with a passage and it must answer questions based on the content of the passage. SQUAD comes in two versions. Version 1.1, the model must extract a span of text from the passage that answers the question. Here, the context always contains the correct answer. In version 2, it is built on the version 1.1 by introducing unanswerable questions, requiring the model not only to extract answers but also to determine when no answer is present in the passage. In our approach, we fine-tuned RoBERTa solely using the provided score training data, unlike other models that may rely on additional training data or data augmentation. The third benchmark is the RACE benchmark, which stands for Reading Comprehension Dataset. It consists of a set of questions based on passages where models must select the best answer from multiple choice options. It is a large-scale reading comprehension dataset with over 28,000 passages and nearly 1 lakh questions collected from English examinations in China, designed for middle school and high school students. The task assesses both reading comprehension and inference skills, challenging the models to understand complex passages and select the correct answer among several distractors. Now let's discuss the performance of RoBERTa across the three benchmarks. Firstly, for glue, it is important to mention that for the development stage, the median of 5 individually trained models was taken as the final output, while for the ensemble, 5 to 7 models were trained per task. In the first setting, which is single task development phase, RoBERTa achieves state-of-the-art results on all 9 glue tasks. In the second setting, that is the ensembles or the test phase, RoBERTa was submitted to the glue leaderboard and it achieves state-of-the-art results on 4 out of the 9 tasks, which are MNLI, QNLI, RTE, and STS. For SQUAD, RoBERTa performed exceptionally well, particularly on SQUAD 2.0, where its ability to interpret contextual clues allowed it to excel in discerning both answerable and unanswerable questions. This led to high scores in exact match and F1, two key metrics for evaluating question answering systems. The exact match score reflects the percentage of predictions that exactly match the ground truth answer, while F1 score is the harmonic mean for recall and precision, making it an important indicator of the overall performance. RoBERTa outperformed on all but one single model submission, securing its place as the top scoring system among those that did not use any data augmentation techniques. In the table, we can see that the plus marks the models that use data augmentation or extra data for tuning their models. For race, RoBERTa achieves state-of-the-art performance on both middle school and high school subsets of the race test sets. RoBERTa's strong performance on the race highlights its ability to not only retrieve information from passages but also comprehend the underlying context, making accurate inferences to choose the correct answers from challenging multiple choice options. In conclusion, RoBERTa's performance across glue, squad, and race underscores its effectiveness in various natural language understanding tasks. Its robust training on extensive datasets, dynamic masking, and fine-tuning strategies equip it to excel in comprehension, inference, and reasoning tasks. This positions RoBERTa as a leading model in NLP.
Hi, Nisha here, and let's sum up all of the results that we got into conclusions. So we found that pre-training BERT for longer gave significant improvement, even beating models such as XLNet, which are larger. Additionally, if we used a batch size that is not too large, not too small, the batch size of 2K, then that gives the best performance. And using byte pair encoding can add additional parameters to this, thereby improving the performance. Removing the NSP loss matches or slightly improves the downstream task performance in contrast to the original BERT paper that was proposed by Devlin and others. If you use dynamic masking, then that gives us marginal improvements in terms of performance, but it's very useful if you're going to do a lot of pre-training or use a large amount of data. So these modifications give the result that RoBERTa actually surpasses BERT in multiple benchmarks without overfitting to the training data. These modifications prove that BERT was undertrained, and with the right optimizations, even better results can be observed. So, the success of RoBERTa underscores the importance of careful model design and the impact of training decisions that we make, thus pushing the boundaries of natural language processing. Thank you. Um, and these are all the resources that we have referred to.